Thank you all for joining. So today we're going to discuss about solitary patterns in R graphs through the lens of CLM's dependence relation. So before that, I'm going to motivate and give a definition of R graphs. For that, I discuss a couple of questions just to understand the motivation behind the definition of R graphs. After that, we'll go into the solitary patterns in R graphs through the lens of CLM's dependence relation. So let's try to understand what's the definition of R graph. We'll start with that. Okay. So we all know regular graphs, right? Here are three regular graphs. That means degree of each vertex is 3. So these two are the examples of three regular graphs. Clearly, one of them is 3-edge colorable, and the other is not. This we all know. Petersen graph is not 3-edge colorable. Okay. Let's ask the following question: which R regular graphs are r-edge colorable? So it is easy to observe that if you take any R regular graph, we need at least R colors to color the graph. So edge chromatic number is at least R, and the equality holds if and only if the graph has R pairwise disjoint perfect matches. So in light of this observation, we can restate the above question as follows: which R regular graphs have R pairwise disjoint perfect matches? So just to recall, here is a 3 regular graph with a perfect matching. Perfect matching means a set of edges. Here they are red edges, such that each vertex has precisely one red edge. And this 3 regular graph is also 3-edge colorable. Okay. So if you want to know all R graphs that are r-edge colorable, it's clearly this is a non-empty set. So let's see this graph. Is it 3-edge colorable? So before that, we'll ask a simple question: does this graph has a perfect match? By our previous observation, a 3 regular graph is 3-edge colorable if and only if it has 3 pairwise disjoint perfect matching. If you observe carefully, this graph does not have a perfect matching, therefore it is not clearly 3-edge colorable. So what about this? This graph has a perfect matching. We can take these 3 edges, but does it imply it's 3-edge? It's r-edge colorable. Here r is equal to 5. It is not, because to color this triangle 6 edges, we need at least 6 colors. So it is not r-edge colorable. Here r is 5 regular graph. Okay. So it's not also about multiple edges. So let's take this simple graph. This is a 3 regular graph, but this is not 3-edge colorable. So we'll ask the following question: is there a necessary condition to be an R regular graph to r-edge colorable? So it turns out to be something related to cuts is going on here. Let's see. Let's recall the definition of cut, and then we'll proceed. Yeah. So a cut is a set of edges from x to x bar, where x and x bar is a partition of vertex set. So we denote partial of x as a cut corresponding to what this x. That means precisely one edge in x and another edge in x bar. So here are 2 cuts. We say a cut is even if both of its shores I mean x and x bar are even, or otherwise it's an odd cut. So C is an even 3 cut. This 3 represents the cardinality of the cut, and so D is an odd 3 cut. Right? So for an odd cut, we need at least one of the shore to be odd. It's a complement of even cut. Okay. So let's G be any graph and C is an any odd cut. So can we observe something about a perfect matching intersection this odd cut? It's easy to observe that by just parity, every perfect matching meets every odd cut at least once. Right? Yeah. So let's recall if an r-regular graph is r-edge-colorable if and only if it has r pairwise disjoint perfect matchings. So by just using this above observation, we can conclude the following. If an r-regular graph is r-edge-colorable, then size of each odd cut should be at least r. If you have a small odd cut, then clearly it can't be r-edge-colorable by these two observations. So this is a necessary condition. That's where the definition of R graphs comes into picture. So it's easy to observe that the converse is not true. This is only necessary but not sufficient. Petersen graph is the same example. So we started with this question just to understand the definition of R graphs, and we rephrased this question as follows. And now, because of this necessary condition, it's sufficient to focus on this question. Which are regular graphs with an additional property that size of each odd cut is at least r or r-edge-colorable? If this condition fails, then it directly implies it can't r r-edge-colorable. So therefore, we are naturally imposing this condition. So turns out to be these graphs are well studied, and clearly these graphs are R graphs. This is the definition of R graph. So we say graph is an R graph if it is connected R regular on at least 4 vertices. Order means number of vertices. And more importantly, size of each odd cut is at least R. So in the rest of the talk, we are going to discuss about R graphs. So this is the definition of R graph. So now we can rephrase this question like this: which R graphs are r-edge-colorable? Yeah. So note that we are not going to solve this question. This is a very classical, difficult problem. So I just motivated you to understand clearly the definition of R graphs. These R graphs are r-regular graphs which are connected and has at least 4 vertices with the natural restriction that size of each odd cut is at least R. That's it. Connected is technical, but just some results we are putting connected and 4 or more vertices. We can even discard that. So recall the famous Tutte theorem. If you take any simple graph, it can be colored using delta plus 1 colors, where delta is the maximum degree. So note that this is only for simple graphs. So Seymour 1977 conjectured that if you take any R graph, not necessarily simple, we can color this using R plus 1 colors. So this is a conjecture because the previous physics theorem we saw, it's only for simple graphs, but R graphs may not be simple. Just to recall the definition of R graphs, here we are not putting any restriction on simple graphs. So here are 2 examples of R graphs. This is simple 3 regular graph, but still it requires 4 colors. This is 4 regular graphs, but not simple, but it requires only 4 colors. That you need to observe. Yeah. So from the famous Tutte one-factor theorem, we'll get as a corollary that each edge in an R graph belongs to at least one perfect match. Let's summarize till now what we have seen. So R regular graphs are a big class. In that, R graphs is a subclass. All r-edge-colorable graphs are completely contained in R graphs. So for an R regular graph to be r-edge-colorable, it must be an R graph, but it's just a necessary condition but not sufficient. So from now onwards, we're going to see, we're going to study some type of edges in R graphs. So just to recall, each edge in an R graph belongs to at least one perfect match. Now we are interested in the type of edges where it belongs to exactly one perfect matching. Turns out to be this. Let's see the definition of the edges. Yeah, we say an edge E is solitary if E belongs to exactly one perfect matching. So one natural question one may ask is there an upper bound on number of solitary edges in R graphs? So let's take an example. So this is a 3 graph. If you observe carefully, you'll realize that every red edge is a solitary edge. That means if you take any edge and ask how many number of perfect matchings containing that edge, they are precisely one perfect matching. So here in this example, we have n over 2 solitary edges. So in general, in an R graph, number of solitary edges may be linearly many. But if you observe carefully, there is a small cut here. It's an even 2 cut. Even means on both shores, even number of vertices, the cardinality of the cut is 2. Okay. So an immediate question we can ask is, what if we bump up the connectivity? Instead of studying R regular graphs, what if we study 3-edge connected R graphs? Turns out to be there are some earlier works. So Goalkeeper, Mattiello, Mazzucchello, Renders, and Wolf proved that every 3-edge connected R graph has at most 6 solitary edges. Yeah. Every 3-edge connected 3 graph has at most 6 solitary edges. And they also gave a complete characterization of all 3-edge connected 3 graphs with at least 3 solitary edges. So our contribution is, we proved the following. If G is any 3-edge connected R graph, if R is equal to 3, then G has at most 6 solitary edges. If R is at least 4, then G has at most 4 solitary edges. And we gave a complete characterization of all 3-edge connected R graphs with at least 3 solitary edges. So I think the problem statement is clear. Now in this talk, I'm going to present a proof of first 2 parts of the this theorem. So for that, we are using CLM's dependency relation theory. So now we'll look into that. So to prove our main contribution, we are heavily using the CLM's dependency relation theory. Now let's see what this theory is. Before that, is a problem statement clear? Any doubts? Okay, let's proceed. So recall that from Tutte's one-factor theorem, we will get a corollary that each edge in an R graph belongs to at least one perfect matching. So these graphs are well known. A graph is said to be matching covered if it is connected and it has at least 2 vertices. More importantly, each edge belongs to some perfect matching. Therefore, R graphs are matching covered. So Carvalho, Lucchesi, Murty in 1999 formally introduced and studied the concept of dependency relationship between the edges in a matching covered graph. We say an edge E depends on edge F if every perfect matching containing E also contains F. And we say edges E and F are mutually dependent if both E depends on F as well as F also depends on E. So this is an equivalence relation. You can take a moment and think about it. So to get familiarized with the notion of dependency relation, I will give one example and we can walk through the example. Let's take this graph and ask the following question. So does D depends on E? That means, is it true that every perfect matching containing D also contains E? No, this is not true because I can show you a perfect matching containing D but not containing E. What about this? Yes. Clearly, if you take any perfect matching that contains E, it also contains D. So what about this? Again, no. So this is interesting. Maybe we can try this. If I take one minute. So meanwhile, you can think about that. So what is the answer for this? So if you take any perfect matching containing E, it will contain D from 2 and then it should contain this edge and then G. So E depends on G. And here G also depends on E by the same reasoning. If you take G, it contains this, and then D, and then E. So what about this? No. Okay. So I hope you convinced that mutual dependence is an equivalence relation. Therefore, it partitions the edge set into some equivalence classes. In the whole talk, with respect to this relation, we are calling the equivalence classes as an equivalence classes. Okay. Now, if you take these equivalence classes along with the depends on relationship, it will form a poset. Let's see the poset corresponds to this graph. So for this graph, we have 10 equivalence classes. 2 of them are size 2, and remaining all are size 1. So in this poset, if it is a minimal element, then we are calling that equivalence class as a minimal class, the usual way. Okay. So in a matching curve graph, this is just an observation. Any perfect matching is the union of some equivalence classes. That means if you take any perfect matching and any equivalence class, either the class, everything in the class should contain, or none of the edges in the class will contain. So, yeah. If E depends on F and F is solitary, can we conclude something about E? So our graph is a matching curve graph. That means each edge belongs to at least one perfect matching, and also the edge E depends on edge F. That means every perfect matching containing E also contains F, and F is solitary. That means number of perfect matchings containing F is exactly 1. So can we conclude something about E? How many number of perfect matching does E contain? Exactly 1. Yeah. And F also depends on E. So this is a very simple observation, but this is useful. So in light of this this observation, we can classify equivalence classes into 2 types: solitary class and non-solitary class. And every solitary class is a minimal class. This directly comes from this observation. Suppose a solitary class lies something here above, and then this depends on this, and this also depends on this, and they will collide club into a single equivalence. What about the converse? So, is it true that every minimal class is also solitary? The converse is not true. We're going to show an example. Yeah, let's take this graph, and the poset corresponds to this graph, and observe that the edge 4, 5 is a minimal class here, but I can show you at least 2 perfect matchings containing edge 4, 5. You can take this green cycle and alter. Okay, so the converse is not true. And also, if you take any perfect matching, it has at most 1 solitary class. So this is also just an observation. If it has 2, then they both depends on each other, and they will become 1 solitary class. As a corollary, we will get the following: for any r-edge-colorable r-regular graph, in the case of r-regular graph, r-edge-colorability means it has r pairwise disjoint perfect matchings. From this corollary, we will get that it has at most r solitary classes, because each perfect matching has at most 1 solitary class, and if it is r-edge-colorable and r-regular, that means it has r pairwise disjoint perfect matchings. Therefore, it has at most r solitary classes. So, Lucchesi and Murty proved that any minimal class of size at least 3 contains an even 2 content. So recall that minimal classes are the minimal element in the poset. Okay. Let's take an example. This is a 3 graph. This we have already seen, and each red edge is a solitary edge, and hence this the red edges class forms a minimal class. Every solitary class is a minimal class. We just observed before, and the converse is not true. So here, by this, what this theorem is saying, if you take any matching curve graph that has a minimal class of size at least 3, clearly number of red edges is at least 3. Therefore, it should contain an even 2 cut. Here, there is an even 2 cut. Okay. So, as an immediate consequence of this, we'll get the following. If you take any 3-edge connected matching cover graph, size of every minimal class is either 1 or 2. Because it's a 3-edge connected, can't have even 2 cuts. Therefore, just a contrapositive of the above. Okay. So let's put everything together. What we have observed till now. This just we saw as a corollary of Lucchesi and Murty. And if you take any r-edge-colorable r-regular graph, it has at most r solitary classes. And each solitary class is a minimal class. That means if you take any 3-edge connected r-edge-colorable r-regular graph, it has at most 2 r solitary edges. So we'll take a moment and observe why this follows from these three. So here it says, if you take any r-edge-colorable r-regular graph, it has at most r solitary classes. Here it says, if you take any 3-edge connected matching cover graph, size of each such class is either 1 or 2. So therefore, 2 times r, at most 2 times r solitary edges will get. Okay. So just a definition, we're calling solitary class of size 1 as a solitary singleton and size 2 as solitary doubleton. So this is our main theorem. To take any 3-edge connected R graph, size of each solitary class is either 1 or 2. That we just observed. It's a corollary of Lucchesi and Murty. And if R is equal to 3, then G has at most 3 solitary classes. If R is at least 4, then G has at most 2 solitary classes. In this talk, I'm going to give a proof of the main theorem. So as a consequence, we'll get these solitary patterns. So before that, what is a solitary pattern? Solitary pattern is a sequence of cardinalities of solitary classes. So here, the second part says, if you take any 3-edge connected 3 graph, it has at most 3 solitary classes. That means these are the cardinalities of the classes. So we can have at most 3 tuple or 2 tuple or 1 tuple. And the first one says the cardinality of each such class is either 1 or 2. So therefore, these are the only possible solitary patterns. So first 4 happens only for r is equal to 3 from the part 2, and yeah. So now we are going to prove part 2. That means if you take any 3-edge connected R graph, then it has at most 3 solitary classes.
Also, the empty pattern is possible.
Yes, yes. Empty pattern means there is no solitary edges. Therefore, we can have empty pattern. For example, if you take a Petersen graph, each edge belongs to at least 2 perfect matchings. Therefore, its solitary pattern is empty. So, to prove the part 2, what we are going to show is, if an R graph has a solitary edge, then it is r-edge-colorable. If you put r is equal to 3, then it will have at most 3 solitary classes, because it's a three regular graph that is 3-edge colorable. Therefore, it has 3 pairwise disjoint perfect matchings, and each perfect matching has at most 1 solitary class. Therefore, it has at most 3 solitary classes. So to prove 2, our next goal is to prove the moment if an R graph has a solitary edge, then it is r-edge colorable. So before going to that, we want to look the structure of an R graph with respect to a solitary edge. So let's see structure of an R graph with respect to a solitary edge. G be any R graph and E is a solitary edge in G. So Kotsik 1959 proved that every graph that has a unique perfect matching has an odd one cut. What is an odd one cut? It's a cut edge with both shores as odd number of vertices. Okay. So why we are discussing this here? Because by the definition of solitary edge, number of perfect matchings containing E is exactly 1. So therefore, the moment we remove the ends of this edge, the resultant graph has exactly one perfect match. By positive result, it has an odd one cut. So this is our odd one cut. That means this set is odd and this set is also odd. Okay. So let's put our UV back. Can we argue the sizes of these cuts, C and D? Do we know anything about the sizes of cut C and size of cut D? So let's recall the definition of R graph. Size of each odd cut is at least R. By this result, this is an odd set and this is also odd set. So this cut corresponding to X is at least R, and this is also partial of X is odd and partial of Y is also odd. I mean at least R. And number of edges going outside from U is R minus 1. This is also R minus 1 because E is already here. And number of edges here going out from X other than E, F is at least R minus 1, at least R minus 1. If you do the math, you will realize that the size of cut C is R and size of cut D is also R. Because from X, it needs to come at least R minus 1 edges, at least R minus 1 edges from Y. And here also we need R minus 1 and R minus 1. So C and D are R cuts and also odd cuts, odd R cuts. Okay. Yeah. So for any R graph with a solitary edge, it has one of the two following patterns structures.
Why are both sides odd?
Yeah. So it comes from yeah. So R graph is matching covered, right? That means it has a perfect matching, therefore both sides. So if you take any R graph with a solitary edge, then it has one of the two following patterns structures. So in one case, we will get all the edges from U other than E will go to one side, and from V will go to other side. In this case, we will get a 2 cut containing E. And in other case, at least one edge from U will go to X and Y. The same with B. So this is clear. The moment we have a solitary edge in any R graph, the structure of that graph with respect to a solitary edge will look like this. So we came to know the structure of the graph just to prove if a R graph has a solitary edge, then it is r-edge-colorable. Now let's prove that. So before going to that, we can see an immediate consequence of this. If you take any R graph that has a solitary edge, and ME is the unique perfect matching containing edge E, then the multiplicity of each edge in this perfect matching is exactly 1. So let's take a moment and observe why this is true. So from this structural result, it is clear that multiplicity of E is 1. Multiplicity, I mean number of edges joining U and E. So for edge E, it is very clear. What about other edges in the unique perfect matching containing E?
It's not just for 3. So,
Yes. This is for all R graphs. So for all other edges, also the multiplicity is 1 because if it has 2, then we can switch the perfect matching containing E with those 2 multiple edges. So now our aim is to prove the following. In any R graph, if it has a solitary edge, then it is r-edge-colorable. So as usual, we are going to prove this by induction. From our structure result, R graph should look like one of these two. We'll do induction on number of vertices. What happens if cardinality of X is 1 and also cardinality of Y is 1? Then these two graphs look like this. Yeah. If cardinality of X is 1, all these edges will go here and all these edges will go here. And then the same for this. It is easy to observe in this case, these two are r-edge-colorable because it's C4 plus 1 perfect matching multiplied. It's a K4 plus 2 perfect matchings multiplied. So you'll get the color classes like that. So in the other case, at least cardinality of x, at least one of x or y is strictly greater than 1. Let's assume, so I'll show proof for this, the same goes through here. Let's assume cardinality of x is at least 3. And now we are going to shrink all this x into a single vertex and all this x bar means y union uv into a single vertex. And we will get two smaller graphs like this. What we did, we just shrink this x and we will get this graph, and we shrink x bar, we got this graph. It's very clear that both graphs are regular because this is r cut. So if we shrink, the degree of this small vertex is also r. If we take a movement, we will also realize that the size of each odd cut here is at least r. If not, the same odd cut will be an odd cut in the original graph. It contradicts the definition of r graph. It's a counting argument.
It's going out of C.
Exactly. So this is a solitary edge, and if you remove both ends, you'll have a odd one cut. So therefore, x is odd, y is odd. And we know, since this is an R graph, number of edges going outside from x is at least r. So, and number of edges going outside from y is also at least r. And what about this? This is also r regular. So number of edges going outside from here other than this edge is r minus 1. And for this also r minus 1. To make it at least r, here we have only 2 times r minus 1. So it should be r. Yeah. So these two are smaller r graphs, but to apply induction hypothesis, I need to show existence of a solitary edge in both the graphs. Now I claim that E is solitary in this graph and F is solitary in G shrink X bar. So why this is true? Because if you take any perfect matching containing F in G shrink X bar, and if you take any perfect matching containing E in G shrink X and take the union, it's a perfect matching in the original graph. If at least one of them is not solitary in these two graphs, then it contradicts the assumption that E is solitary in the original graph. So by induction hypothesis, these two smaller graphs are r-edge-colorable. So therefore, in one of the graphs, we can adjust colors so that our original graph is also r-edge-colorable. So is this proof clear? Okay.
Why can you apply induction on both of them? Only so you had the case when x and y have sizes 1 both each, right? But for both of them, the size may not decrease.
No, it will.
The number of both.
So here, I'm shrinking x.
Okay.
So this is odd. Odd means at least 1.
Okay.
I'm in the case that cardinality of x is at least 3. So if I shrink, this graph is definitely smaller. And if I shrink all x bar includes u1. This proof is clear? So we'll get this as a corollary. Any R graph that has a solitary edge, we can color using exactly R edges. Edge chromatic number of that R graph that has a solitary edge is exactly R. So recall Seymour's conjecture that he conjectured this is we can color any R graph with r+1 colors. So we just showed that if it has a solitary edge, we are able to color using R colors. There is no connectivity condition here. Okay. So yeah, we observe we are done with the part 2. We just show that if a tree graph has a solitary edge, then it is 3 edge colorable, and if it is 3 edge colorable, it has at most 3 solitary classes. Okay. Yeah, just recall this what we have discussed here. So now our goal is to prove the third part of the main theorem. If R is at least 4, now I am going to show that it must have at most 2 solitary classes. With the help of this r-edge colorability, what we will get is if R is at least 4, we can get at most R solitary classes because it is r-edge colorable and each color class has at most 1 solitary class. From at most R to we are going to reduce to at most 2 solitary classes. So that's our next goal. Yeah. So we proved the following. If you take any 3 edge connected R graph that has a solitary edge, then for each vertex in the graph, there exists a triangle such that so vertex is not in the vertex set of triangle, and the graph induced by the vertex set of triangle has precisely R edges. In other words, number of edges going outside from the triangle is exactly R. So what is this saying? If you take any 3 edge connected R graph that has a solitary edge, and if you pick any one vertex, I can show you a triangle not containing that vertex. Here it is this triangle, such that number of edges inside this triangle is exactly R. If you take for example, if you take R is equal to 5, the number of edges in the triangle is exactly 5. Therefore, by counting, number of edges going out from the triangle is exactly 5. So we proved this. If you can prove this using the same technique. You take the structure of R graph with respect to a solitary edge and consider the cases. What happens if both cardinality of x and y is exactly 1? Then you will get C. You won't get C4 here because it's 3 edge connected. You will get K4 with multiple perfect matchings. Then that's the base case, and you can take the 2 smaller graphs as usual, as we did for the r-edge coloring. Then we can easily prove this by induction. Okay. As a corollary, we'll get the following. If you take any simple 3 edge connected R graph, yeah, so this is T, W is anything outside. If you take any W, I can show you one triangle not containing W with the following property. I can show you other triangle. Yeah. For each vertex, I can show you a triangle not containing that vertex with the following property. Okay. Yeah. We'll get a consequence. This if we take any 3 edge connected simple R graph where R is at least 4, then each edge belongs to at least 2 perfect matchings. Let's take a moment and see why this is an immediate consequence of this. So from this, we can get a triangle like this in the graph, such that inside the triangle edges is exactly 4. I mean, at least 4. So if R is at least 4, we'll get at least one parallel edge. So the graph cannot be simple. So if we take any simple 3 edge connected R graph, then each edge belongs to at least 2 perfect matchings. Okay. Yeah. Now we are going to show that if if you take any R graph, or at least 4, and if it has a triangle, the rainbow triangle, that means number of edges inside the triangle is exactly R, and number of edges going outside the triangle is also exactly R, then that graph has at most 2 solitary classes. So if I take a triangle like this, if my R is at least 4, then inside the triangle I have at most 2 simple edges. So therefore, by using this corollary, just recall the corollary. If we take the unique perfect matching containing a solitary edge, then the multiplicity of each edge in that perfect matching is exactly 1. So here, the moment R is at least 4, then we can have at most 2 simple edges. Therefore, by this corollary, at most 2 solitary classes. In particular, here in the red perfect matching, we can't have any solitary edge by this. Likewise, blue and the green. So now we also proved the third point. If R is at least 4, then G has at most 2 solitary classes. And this combining with part 1, we will get these number of solitary edges as a consequence. Okay. So these are the possible solitary patterns for any 3 edge connected R graph, and the first 4 patterns possible only when R is equal to 3. Now we are going to show our results, what we have done, all the characterization for 3 edge connected R graphs for the following solitary patterns. Okay. So we proved the following. Only 3 edge connected R graphs with the solitary pattern 2, 2, 2 or K4 and C6 bar. Color classes represent solitary classes. Okay. So the only 3 edge connected 3 graph with the solitary pattern 2 to 1 is S8, the Python graph, and for 2, 1, 1, S10, this is the only graph. And for the solitary pattern 1, 1, 1, we have 5 graphs. We are going to display them in the next slide. For solitary pattern 2, 2 and 2, 1, this is for all 3 edge connected R graphs. These are infinite families. I'm going to show how they look like without formally defining them in the next slides. So these are open, and we solved this for the case of R is equal to 3. We gave a recursive characterization for 3 edge connected 3 graphs for solitary pattern 2. So these are 3 edge connected R graphs with solitary pattern 1, 1, 1. These 5 graphs. This is a characterization of all 3 edge connected R graphs. Here, of course, R is equal to 3 with solitary pattern 1, 1. So if a 3 edge connected R graph has a solitary singleton and solitary doubleton, then it is a 3 staircase of thickness R minus 2. So what is a 3 staircase? 3 staircase looks like this. We can generalize the construction, and this is of thickness 1. What is thickness? I will define. So alpha, beta and E stays here, and if you take the perfect matching containing alpha and take perfect matching containing E, you are left with exactly one perfect matching, because this is 3 edge colorable. That is like green perfect matching. If you want the graphs with thickness 2, you just multiply this green perfect matching. If you want thickness 3, you multiply one more time the green perfect matching. In this way, so these are, if any 3 edge connected R graph has a solitary singleton as well as a solitary doubleton, so those graphs will look like this. These are like 3 staircases of thickness R minus 2. And R is our R graph. So if a 3 edge connected R graph has at least 2 solitary doubletons, then it is a 1 staircase of thickness R minus 2. So what is 1 staircase? Here are some 1 staircases, and again, if you alpha prime, beta prime stays here. As usual, you take a perfect matching containing alpha and beta, you are left with the unique perfect matching, because our graph is r-edge-colorable. Here R is equal to 3. That is green perfect matching. If you want thickness 2 graphs, you just multiply the green perfect matching. It looks like this. So I'm going to show you a proof sketch of this. Like this theorem. The moment if you take a 3-edge connected R graph, at least 6 vertices, this is just a technical condition, then it is a one staircase of thickness R minus 2. Yeah. So this is our next goal. And for that, we are assuming 3 lemmas. So after that, we are ready to prove this. Okay, let's see the required stuff. Yeah. So as a first step, we proved the following. If you take any 3-edge connected R graph that has a solitary doubleton, then G minus that solitary doubleton edges is a bipartite matching cover graph such that ends of both alpha lies in one color class and ends of beta lies in other color class. Yeah. To put it simply, if you take any 3-edge connected R graph with the solitary doubleton alpha beta, the moment you remove alpha and beta from the graph, it's a bipartite matching cover graph. So here is a concrete example. So red edges are alpha beta. If you remove, we can color the graph with 2 colors. So we also proved that if you take any 3-edge connected R graph with 2 solitary doubletons, then it has a subgraph J such that J is a dumbbell of thickness R minus 2. What is a dumbbell? So this is a dumbbell and this is also a dumbbell of thickness 1. These are the dumbbells with thickness 2. These are the dumbbells with thickness 3. And furthermore, these alpha, beta, alpha prime, beta prime are the only unmatchable edges of this dumbbell. That means if you take any edge other than these 4 edges, there belongs to at least one perfect match. These 4 edges are only the unmatchable edges. That means there is no perfect matching containing any one of these 4 edges in this double graph, not in the whole graph. Okay? And this is well known. If you take any bipartite graph with a unique perfect matching, of course non-empty, then you can find a degree 1 vertex in both the color classes. Yeah. So now we are ready to prove our theorem. Yeah. Just to recall, we have a 3-edge connected R graph with 2 solitary doubletons alpha beta, alpha prime, beta prime. Now we are going to prove that it is a one staircase of thickness R minus 2. Okay. So we're going to prove our graph something looks like this. For the sake of proof, I'm taking R as 5. The proof goes for any R. So our G is a 3-edge connected R graph with 2 solitary doubletons alpha beta, alpha prime, beta prime. By dumbbell existence lemma, there exists a dumbbell. So we are taking maximal dumbbell. And recall that these 4 edges are these 4 unmatchable edges here. Okay. Now, solitary doubleton lemma, we discussed that G minus alpha minus beta is bipartite matching cover graph. That means I can color the vertices and the color only violates for alpha and beta. Let's take a coloring. So black and white. So right now we don't know whether the vertex set of this J maximal dumbbell is equal to vertex set of G or not. That we don't know. We just colored for this J. Okay. Yeah. So suppose there is an edge between, if there is an edge between U1 and W2, are we done? We want to show that a graph something looks like this. And suppose if there is an edge like this, our graph is phi regular. Every vertex in this graph other than W1 and U2 are saturated. And our graph is also 3-edge connected. Done? Yes. Yes, we must have that edge. Otherwise, these 2 edges forms a 2 edge cut, contradiction to our assumption that it's 3 edge connected. Therefore, this it must exist, and we are done. What if there is no edge between U1 and W2 and W1 and U2? Okay, let M denote the perfect matching containing alpha and beta. Let's take that restriction of M here. This is unique. We know perfect matching containing alpha and beta is unique because alpha is solitary. Okay, and the M edge incident at U1 should go outside. Now we are considering this subgraph J prime. J prime is nothing but J plus this extra edge WU1, and we'll remove W2. So if you observe carefully, both J prime and G minus V of J prime has a unique perfect matching. Yeah, that is because alpha is solitary. If at least one of J prime or G minus V of J prime has at least 2 perfect matchings, we will get 2 perfect matchings containing alpha. And G minus V of J prime is also non-empty bipartite. Maybe bipartite is clear because we already colored the vertices. Why it is non-empty? We have a W2 outside, so it is non-empty. So we just saw that if you take any non-empty bipartite graph that has a unique perfect matching, there exists a degree 1 vertex in both color classes. So we take a black vertex of degree 1 outside this graph because G minus V of J prime is uniquely matchable and non-empty bipartite. So we have a degree 1 vertex outside. So the degree of B is 5 in the original graph but 1 outside. So 4 edges must come from B to this J prime. So what are the possible candidates to go these edges? So from B, we need 4 more edges compared to J prime. So can we add to any vertex? No, we can't because this is black vertex. We are supposed to add only for white vertices because this is a bipartite graph. Only the exception is alpha and beta. And if you observe carefully, all the white vertices are already saturated other than these two. It's W and W1. So one possibility is maybe we can add like this. So but we'll get a 2 edge cut. So this is not the good choice. So the remaining possibility is this. So are we done now? So is there any contradiction here? So recall that our J is a maximal dumbbell. Now, can we contradict the maximality? Yes, we can. Yes, take this. This contradicts maximality. Just to recall, we gave a proof sketch of this. If for any 3-edge connected R graph, if it has at least 2 solitary doubletons, then G is a 1 staircase of thickness organized. So here is a summary. So we proved that for any 3-edge connected R graph, if R is 3, then it has at most 3 solitary classes. If R is at least 4, it has at most 2 solitary classes, and size of each such class is either 1 or 2. Therefore, we will get the bounds. Number of solitary edges in the case of R is equal to 3 is 6, and for if R is at least 4, it's 4. And we also gave a complete characterization of all of these patterns except for 1, 1 and 1, and for pattern 2 only for the case of R is equal to 3. And we also gave a complete characterization of matching out graphs with the largest equivalence class size is n over 2. So this is also related to solitary classes because the moment you have a equivalence class of size n over 2, it is a solitary class. I gave a proof sketch of this in my teammate talk last time. Yeah. So here is a summary what we done. Of course, in this talk I only presented the proof of main theorem and proof sketch of pattern 2.